Assalamualaikum and hi. So this is Steam Turbine Cycle Chapter 4 and video part 6. In this video, I'm going to explain the last subtopic, which is the ideal regenerative Rankine cycle. Ideal regenerative Rankine cycle. Ideal regenerative Rankine cycle. So heat transfer at relatively low temperature to 2 prime. As you can see, this is the TS diagram, and if you look carefully, the process of 2 to 2 prime is the low temperature heat addition process, which decreasing the thermal efficiency of the system. And from the regeneration, we can use the heat transfer to feed water that's supplied to the boiler. By doing this regeneration, we can increase the temperature of the feed water, and we can increase the thermal efficiency of the system. So the first method is expanding steam in a counterflow heat exchanger built into the turbine. This is the simple diagram of method 1. As you can see here, this is state 1 and this is state 2, and we have a heat exchanger built in the turbine here, and the state here will be 2 prime, which is some sort of preheating before it goes into the boiler, and the output of it is the state 3 and goes into the boiler. However, we have this system have a drawback, which is the design is not practical, since it is difficult to design a turbine with heat exchanger. And the final stage, which is at the state 4 here, output of the turbine will have higher moisture content, which are no good for the uh, turbine blade. And we have another method, which is extracting steam from the turbine at various points. So we call it regenerator or feed water heater. So the advantage is the aerating, preventing corrosion, and the final stage, prevent control large volume of flow rate. So this is the simplified diagram of the feed water heater. As you can see here, this is the feed water heater, and we have two stages of pump. Pump 1 goes into feed water heater, and pump 2. And so this is the ideal regenerative Rankine cycle, and we have two kind of this ideal regenerative Rankine cycle. One is open feed water heater, and the second one is closed feed water heater. Ideal regenerative Rankine cycle with open feed water heater. So this is the simplified diagram of the ideal regenerative Rankine cycle. And what is open feed water heater? It is actually a mixing chamber where the steam from the turbine and from the pump will be mixed, and it has a direct contact, and both of it have the same pressure. So as already said before, it is a mixing chamber. So the outlet, which is the steam from the turbine exit, bleeding at here, which is this is the bleeding of the turbine, and liquid from the pump here will be mixed in this open feed water heater, which is a mixing chamber, and the output of it is saturated liquid, ideal to boiler. Okay, so now we look into the TS diagram. As you can see here, number one here is at the TS diagram at bottom down here. One. Number two, after the pump, isentropic compression from pump 1, it goes to state 2 here, and then it goes into the open feed water heater, and the output of it is state 3 there, and goes into the state 4, isentropic compression from state pump 2, from state 3 to state 4, and then constant pressure heat addition process 4 to 5, and goes into the turbine and bleeding uh, to the open feed water heater, which is the state 6, and goes into the mixing chamber, and the output of it is state 3. Y percent of the mass will be bleed out from the turbine, and the rest of the mass, which is 1 minus y, will goes to the state 7 of the condenser. So as you can see here, the P6 and P2 will be mixing at the mixing chamber of the open feed water heater, and the output of it is state 3. And from the TS diagram, as you can see here, the state 2, state 3, and state 6 is at the constant pressure line. So the pressure of P6 equal to P2 and is also equal to P3. And from this analysis, first we look into the heat transfer analysis. The Q in, which is equal to H5 minus H4 here, H5 minus H4, and the Q out is equal to 1 minus Y, H7 minus H1. This is 1 minus HY, H7 minus H1. This is a constant pressure heat rejection process. Now we look into the work from the pump. Okay, so we have pump 1 and pump 2. Work from the pump, overall pump, which is from pump 1. Here is pump 1 and also pump 2. And the work from pump 1 is 1 minus Y, which is the percentage of mass at state 7 to 1 times the work by the pump in plus work by the pump 2. And work pump 1 in is equal to V, which is the specific volume at state 1 times in the bracket P2 minus P1, and it is also equal to H2 minus H1. And for the work by the pump 2 is equal to specific volume at state 3 times in the bracket P4 minus P3, and it's also equal to H4 minus H3. And the work by the turbine is equal to H5 minus H6 plus 1 minus Y, since Y percentage of the mass is bleeding out and is missing in the open feed water heater. So the rest is 1 minus Y that goes out of the turbine. And so the work turbine is 1 minus Y times in the bracket H6 minus H7. So as you can see, this is the diagram of the turbine. So the inlet of it is state 5, and the outlet from the bleeding is first bleeding in between the turbine is state 6, and then the rest of the steam goes out of the turbine at state 7. So first the mass in at state 5, 1, and it goes into the turbine and still 1, and then Y% of the mass from 1 is bleed out to feed into the open feed water heater, and then the rest will goes out at state 7. So the rest of the mass is 1 minus Y%. So from this analysis, we look into the steam mass per unit mass. You can see, let's say we have a boiler exit 1 kg of steam. From the boiler exit, we have 1 kg of steam. So, and then we have 2 exit at the turbine. One is at the point 6, where Y% of mass goes out or bleed out to feed the open feed water heater. And then the rest, which is 1 minus Y%, will goes along the turbine and out and goes out of the turbine at state 7. So Y is equal to mass flow rate at state 6 divided by mass flow rate of the overall mass, which is at state 5. And then we goes into the mass flow rate system. So the boiler exit has the overall mass flow rate, and the overall mass flow rate is equal to a mass flow rate at state 5, and the turbine exit at point 6 have m dot y mass flow rate, and the rest, which is the outlet at point 7, is m dot times 1 minus y. So please carefully look into this analysis and make sure you understand the difference between y and 1 minus y, and also value of x, which is the moisture content at state 7. Ideal regenerative Rankine cycle with closed feed water heater. So this is the simplified diagram of the ideal regenerative Rankine cycle. And for the closed feed water heater, actually it is a heat exchanger without mixing of the fluid from the turbine and also from the pump. And for this case, we can use different pressure. And as you can see, this is the heat exchanger of the closed feed water heater from steam from the turbine. Okay, so this is steam from the turbine, and this is the liquid from the pump. So this is a cross flow heat exchanger, counter flow heat exchanger, and this is the TS diagram of the uh, closed water feed water heater. And as you can see that point 1 start from this point 1 here and goes into the point 2, and the output of this feed water close feed water heater from the turbine, which is from the steam, and the output of it is a liquid and goes into the state 3 there, and then from state 3 will be compressed by pump state 4, and the output of this mixing chamber from state 2 and state 2 and 4, and the output of it is state 5, and constant pressure heat addition process by the boiler, and the output of it is state 6 and goes into the turbine, and the output of it we have a bleeding at state 7, goes into the closed field water heater, and the bleeding of Y percentage of mass, and the rest, which is the outlet at the end of the turbine process, is state 8, and the rest of the mass, which is 1 minus Y, it goes into the condenser at state 8, and process of the constant pressure heat rejection process happened there at the condenser from state 8 to 1. So as you can see, this is the closed feed water heater, which is the heat exchanger, and from the pressure at state 7 uh, goes into the heat exchanger, and the output of it is pressure at state 3. And as you can see in the TS diagram, so state 3 and state 7 at a constant pressure line, and state 7 will not have a same pressure as state 2. Will be the pressure of state 7 and state 2 is different, and pressure at state 9 and state 3 also will be different. However, pressure at state 7 is equal to the pressure at state 3, and pressure at state 2 is equal to the pressure of state 9, as you can see here. So pressure at state 2 will be equal to the pressure at state 9. So analysis of this system, first we look into the heat transfer process. The Q in is equal to H6 minus H5, and the Q out is equal to 1 minus Y times the H8 minus H1. And for the work pump in is equal to 1 minus Y work from the pump in 1 plus Y time work from the pump 2. And work from the pump 1 is equal to V, which is the specific volume at state 1, times pressure 2 in the bracket, pressure 2 minus pressure 1. And it is also equal to H2 minus H1. And work from the pump 2 is equal to specific volume at state 3 times in the bracket pressure 4 minus pressure 3, and it is also equal to H4 minus H3, and work by the turbine out is equal to H6 minus H7 plus in the bracket 1 minus Y times H7 minus H8. And we look into the steam analysis, which is the boiler exit 1 kg of the steam. So the turbine exit at 0.7 is Y, and 0.8 is equal to 1 minus Y. Y here is the percentage. As you can see, Y is equal to overall mass, not overall, mass at state 7, mass flow rate at state 7 divided by overall mass, which is the output of the mass from the boiler at state 6. And for the mass flow analysis, boiler exit, overall mass is equal to mass flow rate at the state 6. And the turbine exit at state 7, the mass is m dot times Y percentage, and 0.7 is equal to m dot times 1 minus Y. So this is the ideal regenerative Rankine cycle with closed feed water heater, CFWH. So please look carefully between the closed feed water heater and also open feed water heater. The difference between these two is the closed feed water heater, we have a heat exchanger as the heat transfer medium, whereas for open feed water heater is a mixing chamber. Although the closed feed water heater is the heat exchanger, we still have a mixing chamber at the second process. As you can see in this simplified diagram, we have a mixing chamber here. So please keep this in mind and look carefully into these two systems. For your revision, please try to look into all these questions and try to answer it. This is the end of part 6 for chapter 4. Hopefully you enjoy my video, and thank you for your attention.